Okay, so let's remember that Macaulay duration here is a weighted average for the durations of cash flows and security. And the weighted average is based on the present values of the cash flows. So our definition of Macaulay duration here was the sum of the cash flow at time t times the discount factor to the t power. So that's the present value of the cash flow at time t, and that's the weighting of the duration, which is the time at which the cash flow occurs. So here we have a $10,000 zero coupon bond, and we want to compute its Macaulay duration, MACD. So, well, there's only one cash flow that goes on here because this is a zero coupon bond. So there's no coupons, no coupon payments. It just accumulates like a single amount. And it matures in n years, so you've just got one single time payment at time n. So if you looked at a time diagram for this, you've got time 0 here and you've got time n here. And it's a $10,000 zero coupon bond, so 10,000 is the maturity value, so you get 10,000 back at time n, and then you start with your price at time 0. So it's just that one cash flow. We want to find duration, which is the time to the cash flow. Well, this should end up being n. Well, let's use the MACD formula and figure it out. So the cash flow, sum of the cash flows at time t, there's only one cash flow, it's at time n, so this is going to be CFN v to the n. Okay, CFN, the amount of cash flow at time n, is $10,000. And then our discount factor is v to the n, brings it back to time 0. And that's the weight on the duration of that cash flow, and the duration of that one cash flow is n. It occurs at time n. And then we're dividing by the sum of the cash flows, the present values of the cash flows, which is just 10,000 v to the n. And then these guys cancel, and we just get n as we expected. So this is going to agree, this agrees with our standard definition of what duration should be for one single cash flow. It's just the time to the cash flow. All right, now let's look at duration, Macaulay duration for several different assets here. So first, a 5-year zero coupon bond. Well, when it was an n-year zero coupon bond, the duration was n. So here n equals 5, so our duration is just 5 years. It's the time to that one single payment. Now what if you've got a 5-year bond and it's got 4% annual coupons and matures at par? Well, let's look at a time diagram here. So we don't know what the face value of this bond is, but we do know that there are 4% annual coupons. So, and it's a 5-year bond here. So we're going to have payments at time 1, 2, 3, 4, and then it's going to mature at time 5. So the first payment is going to be 4% of the face value. We don't know what face value is, but that coupon payment is going to be F times R. Here R, our coupon rate, is 0.04. So this is just F times R, coupon payment. And then the same thing happens at time 2 and 3 and 4, and then at time 5 we get that last coupon payment, 0.04F, and then we redeem it. And redemption's at par, so we're going to get the face value back again. So what do we do to find duration? Well, we take each one of these cash flows, find its present value, and that's the weighting for the duration, which is the time of the cash flow. So that first cash flow is 0.04F, and if we bring it back to time 0, we're going to multiply by the discount factor V, and then that gets multiplied by the duration of that cash flow, which is 1. Second cash flow at time 2 is going to be 0.04F again. And to bring this cash flow back to time 0 is going to need discount factor v squared. And then that gets multiplied by the duration, which is 2, because that occurs at time 2. And then we keep going here until we get up to time 5. We're going to have that last coupon payment, 0.04f, and it gets brought back to time 0 with a discount factor v to the 5th. And that's the waiting for the duration of that cash flow, which is 5. Let's move our time diagram up here. And then we've got the redemption here, which is the face value. So that's a cash flow of f. Bring it back to time 0 with a discount factor of v to the 5th. So that's the present value of that last, the redemption. And then you multiply it by the duration of that cash flow, which is time 5. It occurs at time 5. And then in the denominator here, we divide by the sum of the cash flows. So the sum of the cash flows here is going to be 0.04f. Sum of the present values of the cash flows. So 0.04fv plus a 0.04f v squared plus ... up to that last coupon payment, 0.04f, and it's at time 5, so discount with v to the 5th, and then our redemption f is discounted with v to the 5th. So this is actually the present value of all those of the bond's cash flows, which is going to be the price of the bond. Now notice here that f is a common factor all the way across the top, and it's a common factor all the way across the bottom. So we could factor that f out and it would cancel top to bottom. So we actually could, if we wanted to, we could take f to be anything we want if it simplifies this calculation. Now factoring it out would leave some decimals in there. But if we took f to be equal to 100, then 100 times 0.04 would be 4. We'd get rid of the decimal. And in fact, that's what we're going to do. So if we take f equals 100, then 0.04f becomes fv becomes 4v. And then 0.04fv squared becomes 4v squared. And so on. So we got 4v cubed times 3, 4v to the 4 times 4, 4v to the 5th times 5. And then our redemption is 100 because we're taking f equals 100, v to the 5th times 5. And then the same thing down here. This is the present value of those cash flows if we take the face value of the bond to be 100. Well, then notice that we've got a common 4 that we can pull out all across the first 5 terms. So I factored that out here. And then I multiplied the 5 in times 100 here, so 500 v to the 5th there. And then we've got a common 4 down here that we can pull out, so 4 times v, v squared, v cubed, v to the 4th, and v to the 5th. And then plus 100 v to the 5th. And then notice this pattern here. This is 1v, 2v squared, 3v cubed, 4v to the 4th, 5v to the 5th. That's the increase in annuity, the present value of the increase in annuity with 5 payments starting with $1, and it increases by $1 each period. So that's just 4 times IA angle 5. And then this factor stays the same, 500 v to the 5th. And then notice v plus v squared, v cubed, v to the 4th, v to the 5th. That is just A angle 5. So this guy up here is just IA angle 5. So this reduces to 4IA angle 5 plus 500 v to the 5th over 4A angle 5 plus 100 v to the 5th. And then I did the calculations using the formula for I angle n and got 12.14. And for A angle 5, I used the A angle n formula, got 4.21. Do the calculator computations here and you get 4.61. All right, what about a 5-year bond with 8% annual coupons? So same situation as we had up here, but now we're doing 8% coupons instead of 4% coupons, still annual coupons. Well, we're going to get this same pattern here, except it's going to be with a 0.08. And then all this is going to be the same, except it's going to be 0.08. So when we get to this step here, the only thing that's going to change is that this is going to be an 8, and this is going to be an 8. So our Macaulay duration in this case then is going to be 8 times IA angle 5 plus, and again, what we're doing is we're doing the same thing. We're taking f equals 100 to make those decimals cancel out. So we're still going to have a 500, because it's a 5-year bond, 5 times 100, v to the 5th. And then downstairs, we get, instead of 4 a angle 5, it's going to be 8 a angle 5. And then the redemption is 100 if we take face value equals 100 v to the 5th. And then I did the well, actually, IA angle 5 we brought down from here, and then A angle 5 right here we brought down. So those stayed the same. And we computed that duration and got 4.34. Okay, doing the calculator work. Now notice that this duration here, all the payments happened with the same spacing. They were just twice as big. We had the payments in the coupon payments were twice as big. Notice that this duration is less than this one. Okay, we'll talk about why that's true here in just a minute, because all that changed was the amounts of the payments, but not the times of the payments. What about a 5-year mortgage with level annual payments? So in this case, all of our cash flows are the same. There are for all values of t. We've got constant cash flows. So what goes on here is one, 2, 3, 4, and 5. We've just got cash flows of R. So instead of a coupon payment of F times little r, we've just got cash flows of R at all those times. So what we do is we take and we bring all of these payments back to time 0, and those are the weights on the durations 1, 2, 3, 4, and 5, which are the times of the payments. So this is going to look like in the numerator here, we're going to take the durations and weight by the present values of the cash flows. So the present value of this one is R times V. So we get RV, and that's multiplied by 1, plus the present value of the second cash flow. This will be brought back with a V squared. So RV squared times 2, plus up to the last one's going to be RV to the 5th. So this one's going to get brought back with a v to the 5th, and that present value is the weighting of the duration 5. And then in the denominator, we're just doing the sum of the cash flows, present values of the cash flows. So this is going to be RV plus RV squared plus ... up to RV to the 5th. So now notice that R is a common factor across the top and a common factor across the bottom. And if we factor this out, on the top we have V plus 2V squared plus 3V cubed all the way up to 5V to the 5th, which is just IA angle 5. And on the bottom we're going to have V squared up to V to the 5th, which is just A angle 5. So our payment cancels out there. And the value of the Macaulay duration in this case is IA angle 5 over A angle 5. And these we already figured in previous parts of the problem, and that ratio is 2.88. And notice that 2.88, that's the smallest duration we've got so far. And then lastly here, what about a perpetuity with level annual payments? So here again, cash flow at time t is R for all values of time. And so if we write out what Macaulay duration is here, it's the sum of cash flow at time t, going back here, cash flow at time t v to the t times the duration, and then sum of the cash flow at time t v to the t. So present value of the cash flows times the durations over the sum of the present values of the cash flows. So still doing that same thing. So here, our timeline is going to look the same as it did up here, time diagram, except it's going to keep going. Alright, so down here, all we need to do is just extend this timeline. And ... So it just continues indefinitely. So it starts out the same way that we did up here. It's going to be R times V times 1 plus R times V squared times 2, present value of the second cash flow times 2 plus ... Keeps going. And then downstairs, same thing. R times V plus R times V squared, except plus ... Continues indefinitely. But then again, R is a common factor, so we can pull that out on the top. What we've got left is V plus 2V squared, 3V cubed, etc. On the bottom, common factor of R can pull out, V plus V squared, V cubed, etc. These guys cancel. On the top, we've just got IA angle infinity. And on the bottom, we've got A angle infinity. And then, you just have to look back here. This might be a little rusty because we're going back quite a ways into the annuities here. IA angle infinity, the present value of a perpetuity with rate I is 1 over I plus 1 over I squared. Present value of the increasing annuity is 1 over I plus 1 over I squared. That's starting at 1 and increasing by $1 each payment period. And then the present value of the perpetuity that has constant payments of 1 is just 1 over I. And then our interest rate here is 0.06. Okay, effective annual rate here is 6% for everything in this problem. So I is 6% for everything in the problem. So then I plugged in 0.6 here, did the arithmetic, 17.67. So let's notice some things. Notice that the Macaulay duration for Part E, the perpetuity, is the largest. And this makes sense because our payments are continuing indefinitely. So if you're taking and weighting the durations by the present values of the payments, well, the durations keep going on to infinity. Everything else, the longest duration was 5. But this isn't an infinite number because as you go out farther, your power on V increases here. So those payments that are out farther get weighed exponentially less in the weighted average. So that's what allows us to end up being finite. But it is larger than all the other durations. Notice that the MACD for A is greater than B, C, and D because it has no cash flows before time 5. Okay, remember that was the 0 coupon? So all your payments for this one happened at time 5. For everything else, we had some payments before time 5 for B, C, and D. So it would make sense that this duration is 5 and these durations were less than 5. So general observation there. And then also notice that the MACD for Part B is greater than for Part C. And that's because in Part C our payments were twice as big. So the maturity value in Part C is going to be actually, this should be B here. Should be the maturity value in Part B is greater relative to its 4% coupons than in Part C with the 8% coupons. So what that does is that gives us a graded weighted average duration. So up here, in Part B, we had 4% coupons. So these values were all multiplied by 4. The only difference down here is that they were multiplied by 8. So if you look at after we simplified here, notice that this number and this one stayed the same down here, but then these numbers here at the beginning, for the 8% annual coupons, these numbers were twice as big as they were here. Okay, so the end duration was larger relative to the 4% coupons than it was the 8% coupons. So that should push this duration out farther. So that's why this is 4.61 versus 4.34. Also, you can actually show with a little bit of work here that the following inequality holds true for all real numbers. If you look at a sum a plus c over a plus b, and then compare it to 2a plus c over 2a plus b. So the c and the b stayed the same here. So in other words, the second part of the numerator and denominator stayed the same, and that's what happened in Part B and C. But then the first part of the numerator doubled. When that happens, that actually decreases the fraction if c is greater than b. So if this numerator was greater than the denominator. And that happened here because we had a multiplier of 5 up here. You multiply by the duration, and down in the denominator we didn't multiply by the duration. So it's actually something that you can show as an inequality with real numbers. And then the MACD for Part D is the smallest because of the ones that had finite payments, because it's got level cash flows for all, actually we had 5 years here, not 10 years. So D was the mortgage here. So we had the 5-year mortgage, and it's got level cash flows, whereas the earlier ones, they had a larger cash flow out at the end. So that bigger cash flow out at the end is going to pull the duration out farther, because the duration is weighted by the present value of the cash flows. Present value of a large cash flow at the end is going to be pulling the duration out towards the end, whereas everything equal, you're not going to have that higher weight in the weighted average. So that's why this one's the smallest. Alright, so let's put some more of this to work here. Look at an example here. On December 31 of 2010, we've got a company that estimates it's going to need to pay $25 million in 2011 and the subsequent years for product liability claims. So could be, say, a pharmaceutical company. They will, when they manufacture a drug and they know that there's going to be issues with the drug, some people may have liability claims against them. So they will set aside money ahead of time to pay these claims. And the payout pattern here is given in the following table. First row is the year, so 2011, 12, 13, and 14. They figure by 2014 they're going to make all 100% of the payouts. So usually a lot of the claims will happen in the beginning, and then if the claims are too high, then they'll do things like pull the drug from the market, or put black box warnings on it, things like that. And then this is the cumulative payout pattern. 75% of the claims of the payouts are going to happen in 2011. 80% total will have happened by 2012, 90% by 2013, and all 100% in 2014. So this is a 75%, an additional 5%, additional 10, and then an additional 10. So we want to determine the duration of the claims if these payments are going to be made at the end of each calendar year. So you can look at a time diagram for this problem here. So let's say that 2011, let's call that time 1, and 2012 time 2, and then 2013 time 3, 2014 time 4. So we've got 0, 1, 2, 3, and 4. And then these percentages are percentages of the 25 million. So at time 1, we've got 75% of the payout. So at time 1, the company is going to pay 0.75 times that 25 million, that fixed amount. Okay, and let's call that fixed amount R. And then at time 2, they're going to pay an additional 5% of that fixed amount. And then at time 3, from 80 to 90%, an additional 10% times that fixed payout. And then at time 4, the last 10% times that fixed payout. Well, this is kind of like what happened with the coupon bonds. And when we figure the Macaulay duration here, these cash flows will all have a common factor of R on the top and the bottom. We can factor it out of the summation and cancel. So we can do the same thing that we did in previous examples and just take this R for purposes of duration, because it cancels out, and just take it to be 100, because then that simplifies what our payouts look like. Okay, so we're going to take our total payout here to be 100. Our Macaulay duration then is going to be our first cash flow. This will turn into 75, 5, 10, and 10. So the first cash flow is going to be 75. We bring that back with a V, multiply it by the duration 1, plus the second cash flow is going to be 5. Bring it back with V squared times the duration 2, plus the third cash flow is 10. Bring it back with V cubed times the duration 3, and then that last cash flow is the last 10%, brought back with V to the fourth and times 4. And then we add the present values of the cash flows below, which are going to just be the 75V plus the 5V squared plus the 10V cubed, and then plus the 10V to the fourth. And now all we have to do is plug in our discount factor. So if we go ahead and plug in V is 1 over 1.06, because our EAR is still 6%. So this is 1 over 1.06. And if you do the calculator work here, you will get 1.49. And you might want to go ahead and double check that. And that's B, just to make sure that you're getting the same answer that I am. So this is actually like one of the FM exam problems. So this is similar to one of the past questions. Oh, and I just wanted to mention this comment up here. When you see the word duration, like up here in the problem, they say determine the duration, and they didn't specifically call it Macaulay duration. So when they say duration, they mean Macaulay duration. And there's another type of duration that we'll talk about called modified duration. And if they mean modified duration, they'll actually specify. So when you hear duration, we're talking about Macaulay duration, weighted by the present values of the cash flows. Now you can actually consider Macaulay duration as a measure of price sensitivity. But how should we define price sensitivity mathematically? Okay, remember, price sensitivity is talking about how things change with small changes in price. So, small changes in interest rates. So here, if we're talking about price sensitivity, we're talking about how fast does the price change as the interest rate changes. So in other words, we want to have some type of derivative with respect to I, the effective interest rate of price, to see how things change. Well, remember that the effective interest rate, or the yield rate, I, which is our horizontal here, and the price vary inversely. Okay, so remember that P varies inversely as I. So that means that as I increases, P decreases, and vice versa. So it also means that if there is a small change in the interest rate, so if there is a positive change in the interest rate, so it changes, say, from 5% to 7.5%, then if you look at what happens to the price, so that's the price at 5%, at 7.5%, notice that the price goes down. So we had an increase here, a positive change in I, and here we had a negative change in price. So that's also because of the inverse relationship. So we don't want our price sensitivity, we don't want this derivative to be negative, because in finance they don't like negative quantities. So what we will look at is, we want price sensitivity to be a positive quantity, so we'll put a minus sign on front of our derivative here. And we're thinking that we want to look at dPdI, the rate of change of price with respect to change in the yield, or the effective interest rate. But then also we want price sensitivity to be a relative quantity. So we want it to be independent of our original price. So we wouldn't want it, large price securities or large price investments to have, different price sensitivity than small investments. Okay, we want to factor that out. So then we're going to take our derivative here and we're going to divide it by P. So then that's going to give us a relative quantity. And in fact, this is what we will do when we figure modified duration. We'll actually figure a negative of the derivative of price with respect to I over price. But here we're going to do our derivative with respect to force of interest first. So we want to define price sensitivity with respect to force of interest to be the negative of a relative change. dP d delta is the rate of change of price with respect to delta divided by price. And here price is just the present value of all the cash flows. So like if you're pricing a bond, the price is the present value of the cash flows. Okay, so recall that when we had a constant force of interest delta, that e to the delta was equal to 1 plus I. So that means that e to the negative delta is v. Okay, we just took negative 1 power on both sides. So then if we want to compute the price or the present value of a series of cash flows under a constant force of interest delta, so I've written this as a function p of delta. So it says the present value at a force of interest delta. Then what are we going to do? Well, we're going to take all of our cash flows and we're going to bring them back to time 0, but our discount factor here now is e to the negative delta. So if this cash flow is occurring at time t, then our v to the t here is v is e to the negative delta, and then that gets a t power on it. So e to the negative delta t is just our discount factor to bring these all back to time 0. And then we want to take the rate of change of price. So we're going to take the derivative, and this is with respect to force of interest, derivative with respect to delta of p, the present value of those cash flows. Okay, so we're taking a delta derivative of this expression. So delta is our variable and t is what we're considering to be constant. So cash flow at time t, that's going to be a constant, and then this is going to be e to a constant, negative t, times the variable delta. So remember, when you differentiate e to a function, take that derivative, you get back e to that function, and then times the derivative of the inside function, so times f prime. Okay, so here we differentiate e to the negative delta t, we get e to the negative delta t. Delta is our variable, negative t is the constant. So we multiply out in front by negative t. That's the f prime of x. So we're just doing term by term derivative, and we still sum them all up. So the derivative of this sum is going to be the sum of the derivatives term by term. and then we just bring the constant cash flows CF of t along. And so then price sensitivity here with respect to force of interest is going to be the negative of the derivative that we just calculated. So this is dp d delta divided by the price or the present value of the cash flow. So this on the bottom is our P. Okay, that was our P from here. So we're just doing this right here. Okay, and then notice that e to the negative delta t, again, that is the same thing as v to the t. And so if I do that substitution on top and the bottom, I have, and then also notice this negative out in front will make that negative, double negative will make a positive. And then here, this is v to the t, and this is v to the t. So now I'm just summing up t v to the t, cash flow at time t, over v to the t, cash flow at time t. And we just do a little bit of rewriting. This is v to the t, cash flow at time t times t, over the sum v to the t, cash flow at time t. Well, this is exactly our expression for MACD, Macaulay duration, right? We come back here. Here it is right here. That's Macaulay duration. Okay, so what does this say? Then price sensitivity, this quantity, price sensitivity with respect to force of interest is the same thing as Macaulay duration. Okay, what we really want though is we don't want a derivative with respect to delta, we want a derivative with respect to I, and that's where this concept called modified duration comes in. So now we want to consider an expression for price sensitivity with respect to I. So now this is going to be an I derivative, derivative of P with respect to I divided by P. So again, a relative derivative, relative rate of change. And then a negative out in front because the inverse relationship between these two variables, this derivative is going to be negative. That's going to change it to a positive. Okay, well, our price here is just the present value of the cash flows. Okay, so this is price here, remember, is just the PV of the cash flows. And then what is the PV of the cash flows? Well, it's the sum of cash flow at time t times v to the t. Okay, so this expression right in here, that's our price. So we're doing the derivative with respect to I of sum v to the t cash flow at time t. And then price down here on the bottom is the cash flows brought back, sum of the present values of the cash flows. And so now this is a derivative with respect to I. Now the cash flows, CF of t, those are just constants. So that's not a problem. But v to the t here, that v is really 1 over 1 plus I. So 1 over 1 plus I to the t is the same as 1 plus I to the negative t. So I realize that we really want to write this as a function of I first before we do our derivative. And so now we've got 1 plus I to the negative t power. This is a function to a power, okay, and we're differentiating with respect to I here. So what we're going to use to compute this is the power rule for functions. So if you differentiate a function to a power, what happens? Well, that exponent comes down in front. Here it is. And to differentiate this sum, we're going to do the sum of the derivatives. And each derivative is the exponent comes down in front, negative t, decrease your exponent by 1, negative t minus 1, and then times the derivative of the inside with respect to I, but that's just 1. And then our cash flows are constant, so they just come along. And then the bottom stays the same because we're not doing any derivative there, we're just dividing by the relative amount. And now we'll switch back to v's because we've got v on the bottom, so 1 plus I to the negative t minus 1, which is actually the negative of t plus 1, is going to be the same as v to the positive t plus 1. Okay, so if you take a reciprocal in here, that changes the sign on the exponent. So now we've got sum of t, v to the t plus 1 cash flow at time t, over sum of v to the t cash flow at time t. And take one of these v's and pull it out in front. So take this one extra v and pull it out in front. And then what we'll have left is v sum of t v to the t cash flow at time t over sum v to the t cash flow at time t. Oh, this is just Macaulay duration right here. So we've got a v out in front right there and MACD. So this price sensitivity that we've found, this price sensitivity, which is what we're calling modified duration, is just V times Macaulay duration. Okay, so if they ask you to find price sensitivity, they'll ask you, what they're really asking you is find modified duration. And the modified duration is just the discount factor times Macaulay duration. Or remember, this is 1 over 1 plus I, so if you multiply both sides by 1 plus I times the modified duration gives the Macaulay duration. So if you're given one of these, you can find the other one. And a nice mnemonic to remember this is, what is modified duration? Well, modified duration is price sensitivity, which is a derivative. Okay, what do derivatives tell? They tell how things change. They tell rates of change. So modified duration here is a derivative of Macaulay. Okay, it's a variation. So you can think here of, to help you remember this, is that modified duration equals the variation or the rate of change. Think of rates of change as variations of duration. And when we say duration, we mean Macaulay duration. So here, V variation, V discount factor. So that can be helpful in remembering that relationship. Now remember from calculus here, when we talked about derivatives, we developed differentials at the same time. And we actually defined differentials and used them to estimate changes. Well, we can do the same thing with modified duration. We can use modified duration to estimate changes in the total present value of the cash flows given small changes in I. So this is coming from, remember when we did differentials here, we would use like the differential of y to approximate delta y, the actual change in the value of a function. And the differential, remember, was f prime of x times dx, where dx was the same as delta x, a small change in the independent variable. So, okay, well, remember here that dp di, the derivative of p with respect to I, is a limit. It's actually the limit of this quantity, change in p over change in I, as the change in I goes to 0. Okay, that's what derivatives are. They're limits of average rates of change. Well, these guys are actually going to be approximately equal to each other if you have small values of delta I. So what that means then is our modified duration then is going to be approximately equal to the negative of change in p over change in I divided by p if you've got, again, small changes in I. Well, the nice thing here is that we don't have to actually figure a derivative here to get this approximation. We can just look at small changes in the effective interest rate and see what kind of effect that has on price, and it can actually be very accurate in predicting what modified duration is, or using modified duration to predict changes in price. So if we take this relationship here and we just solve it for delta p, so multiply both sides by p, multiply both sides by -1, and then multiply both sides by delta I, then you'll get that the change in p is going to be approximately equal to the negative of the modified duration times p times change in I, and again this is for small changes here. And just to note here the negative sign here, again that is referring to the fact that p and I vary inversely. So if we've got a positive change in interest rate here, it gets multiplied by a negative, so that means going to be a negative change in price. If there's a negative change in interest rate here, it gets multiplied by a negative positive change in price. So interest rates increase, price decreases. Interest rates decrease, price increases. And also make a note, modified duration is sometimes referred to as volatility, and that might also be another help in remembering that modified duration is V, the discount factor, times Macaulay duration. Okay, well, let's put this approximation to work here. In example 9.11, we've got a 20-year 1,000 par bond with 4% annual coupons, so annual coupons here. And it currently sells and matures at par. Now this is important. It currently sells at par. We've seen them mature at par, but right now this is saying currently sells. That's saying that P is equal to F. Okay, so and it matures at par. That's saying that P is equal to F is equal to C. So this bond is at a particular price point. So that's something important to this example. We're going to use modified duration to approximate the change in price of this bond if our effective annual rate, okay, this is our I, our effective rate, changes to 4.15%. So right now I is equal to 4%. And remember that if you've got P equal F equals C, that these are 4% annual coupons and this is equal to R. But when you've got P equals F equals C, then R and I are the same, recall. And here's the reason that that's true. So let's lay out our variables real quick. N is 20, it's 20 annual coupons. R is 0.04. P and F and C are all the same, they're 1,000. Our change in interest rate is going to be from 4% to 4.15. So this is the end minus the start. So that's an increase of 0.0015 or 0.15%. So if we look at the cash flow formula for pricing this bond, the price is FR A angle N times C V to the N. Our price is 1,000 here. Our coupons are 1,000 times 0.04, so $40 coupons. And then N is 20, so this is A angle 20 at I. And let's suppose that we didn't realize that the interest rate had to be the same as the coupon rate. And then we're going to discount the maturity value, 20 periods here. So notice that A angle 20 at I is 1 minus V to the 20 over I. So here we've got a 40, and then it's multiplied by 1 minus V to the 20 over I, and then the redemption value 1,000 V to the 20. Alright, well, notice that 1,000 is a common factor here. This is all equal to 1,000. So we could divide that 1,000 off of both sides of the equation. This will be left with a 1 right here. This will turn into a 0.04, and then this will be a 1. So this will be 0.04, 1 minus V to the 20 over I plus V to the 20. Let me move that back over here so you can really see what's going on. Okay, so we want this to be true. And we want to know, well, what interest rate I, what effective interest rate is going to make that true? Well, if I equals 0.04 down here, if the yield is 0.04, then these guys cancel. And then 1 minus V to the 20 plus V to the 20, these will cancel, and we get 1 equals 1. So, and we had talked about this before, so it's just kind of reminding here. If you purchase and you mature at par, then R is going to equal to I, is going to be equal to I. So that's why our I is 0.04. So this is just kind of parenthetical to justify that that's 0.04 right there. Okay, so now let's go ahead and figure our duration here. So duration is the present values as weights of the duration of the individual cash flows divided by the sum of the present values of the cash flows. Okay, so with this bond, we've got 20 cash flows of 40 here. So at time 1, we get our first cash flow of 40. And keep going all the way up to time 20. And then we'll have a cash flow of 40, and then we're going to redeem the bond for 1,000. Okay, so on the top, we're going to bring all of these guys back with factors of v, and then bring the redemption value back with a factor of v to the 20th. And remember what that gives us is it gives us an increasing annuity present value, and then the present value of the redemption. So 40v plus 40v squared plus 40v cubed, etc. I'm sorry, actually 40v plus 40v squared times 2 plus 40v cubed times 3, etc. all the way up to 40v to the 40th times 20. So we're actually going to get the 40 we can factor out, and then we get the increasing annuity for 20 periods, and it's going to be at a rate of 0.04. And then we're going to add on the present value of that $1,000 cash flow, 1,000v to the 20th, and then multiply by the duration of that cash flow, 20. And then down on the bottom here, this is the present value of all the cash flows. That's just the price of the bond right there. That's the price. That's 1,000. And if you do the calculator work here, using the formula for the increasing annuity, you will get 14.133939. So there's our Macaulay duration. And then to figure the modified duration, you just take the discount factor, 1 over 1.04, and multiply it by MACD. So 1 over 1.04 times our 14.13, and you'll get 13.590326. Okay, so then our change in price from this change in interest rate by our approximation formula up here is negative mod D times P times delta I. So that's this formula here. So we've got a negative out in front. Our mod D is 13.590326. And then we're multiplying by our price, which is 1,000. And then our change in interest rate was an increase of 0.0015. And a little work on the calculator here gives a decrease in price of 20.39. Okay, so our price approximation here, this is actually going to be approximately equal to, it was at 1,000 when the effective rate was 4%, and we're going to subtract off, there was a decrease in price of $20.39, and that puts our price at $979.61. Okay, so that's the answer to the first question here. Use the modified duration to approximate the change in price of the bond, and we've actually got the new price. And then we're going to compute the actual change in price and then compare the answers. Okay, so how do you get the actual change in price? Well, you get it from the cash flow formula for the bond. So price is FRA angle N plus CV to the N. Okay, so our face value is 1,000. Our coupon rate's 0.04, and then A angle 20 at 0.0415. Now see our I is changed to 0.0415. And then our discount factor out here is going to be 1 over 1.0415. And that gets a 20th power. And A angle 20 at 0.0415, if you do the calculator work there, you get 13.411. And if we simplify all of this, we get 979.88 for our actual price. So here we got 979.61, here we got 979.88. We're only off by pennies using this approximation. So for small interest rate changes, get a really good approximation. So now actually we wanted to compute the actual change in price, so the actual change, delta P here. Here we approximated delta P as negative 20.39. The actual change in price is going to be the new price, the 979.88, minus the old price. So n minus start. And this gives negative 20.12. So it's just the difference here of about, what is that, 27 cents? So really nice approximation. Okay, now last example with modified duration. Here we have a 4-year $500 par bond. It's got 10% annual coupons and matures at 525.50. If the bond is priced to yield 9.35, determine the duration. So here we have the yield. We want to determine modified duration. Well, to get modified duration, you have to compute Macaulay duration. So what is Macaulay duration? Weight the times of the cash flows with the present value of the cash flows and divide by the present value of the cash flows, which is the price of the bond. Okay, so what happens with this bond? Well, that's 4-year bond. So we got cash flows at time 1, 2, 3, and 4. And it's $500 with 10% annual coupons, so that's going to be cash flows of 50 here at times 1, 2, and 3. And then at time 4 we've got cash flow of 50, and then also the 525.50, which is the redemption value. So what we want to do is, again, take the present value and then multiply it by duration. So here we're going to get 50 times V multiplied by duration 1 plus the second 50 brought back is with V squared times the duration of that cash flow, which is 2, plus 50V cubed times 3 . And let me just go ahead and move this time diagram up here. And then we got that fourth cash flow, 50 V to the fourth times 4, and then the redemption value brought back. So 525.50 present value with discount factor V to the fourth times 5. And then we're dividing everything by the price of the bond. Present value of those cash flows is the price of the bond. Okay, well, let's figure this denominator first. I actually did that down here with the TVM keys. So n was equal to 4, our effective rate's 9.35, our payments, coupon payments are 50, and then our redemption value 525.50, and then I computed the PV. So I priced this thing out at 528.28. So that's our price here, and that's down here. And then I just went ahead and inserted my discount factor all the way along here. And if you do the computations there, you get 1.49 for your Macaulay duration. So then to finish up, we just need to find the modified duration here. And modified duration, mod D, is equal to V times MACD. So that is going to be 1 over 1.0935 is our discount factor, and then times the 1.49. And to 2 decimal places, this is 1.36. All right, then let's look at one last modified duration here. Let's compute the modified duration here for just a normal 30-year mortgage that has payments at the end of each month and has an annual effective rate of 3.66%. So notice that these payments are monthly, and then our annual effective rate, this is an annual rate. So in order to compute this duration here, we got to do something that we haven't had to do before, and we have to make the rate agree with the payment. Okay, so we got an annual effective rate, but then our payments are happening every month. So we need a monthly rate. Okay, so first we need the monthly rate. And so our monthly rate there is going to be I upper 12, which is going to be 1 plus our 0.0366 to the 1/12th power, and then minus 1. And that will give us 0.003. Not exactly 003, but really close. It's like 0.003 and then 000 and some decimal places after that. So we'll just use 003. Okay, so now all of our cash flows here, all of these guys, cash flow at time t, this is a mortgage again, so those are all R, mortgage payment, and all these guys down here, these are all R. And so those are going to factor out and cancel as they did in some of the earlier examples. So this is actually going to be the sum of R times v to the t times t, and then downstairs this will be the sum of R v to the t. These r's are going to factor out and cancel, and so now we're just going to have the sum of v to the t times t over the sum of v to the t. And what's this on the top? Well, that's 1v plus 2v squared plus 3v cubed, etc. That's just the increase in annuity, and it's for 360 months. So this is the present value of the increase in annuity, IA, angle 360, at our interest rate I, and then we're dividing by the sum of v to the t. Oh, that's just A angle 360. I guess I'm not going to write I in there. So it's IA angle 360 over A angle 360. And then, of course, our I here is, our monthly rate is 0.003. So then what's IA angle 360? Well, if we use the formula for present value of the increase in annuity, this is A dots angle 360 minus 360 times V to the 360 divided by I. And then that whole thing gets divided by A angle 360. And then if you invert and multiply, this is just A dots angle 360 minus 360 V to the 360, and then divide by I times A angle 360. And then if you do the calculator work here, figure A angle 360 and A dots angle 360, so that's not hard to do. You will get 220.6115 for A dots angle 360. And then we're going to subtract off 360, and V to the 360 turns out to be about 0.34. So it's actually 340,145. And then downstairs we've got our 0.003. And then A angle 360 to several decimal places is 219,951,6611. And then the final answer to 2 decimal places is 148.76. And that's going to be in months. Okay, because our payment period is months. So that's something that's a little bit different that we hadn't seen before. The thing that was different was we had to convert our rate over. And does this make sense? This is a 30-year mortgage. That's 360 payments. Okay, so if we didn't multiply by the present values, then the duration should be just the average of the durations of all the payments. That'd be half of 360, which would be 180. But remember here that we're weighting by the present values of the cash flows, not weighting the durations by the present value of the cash flows, not just the cash flows. And those present values are going to decrease exponentially as you go out further in the mortgage. So that means that the weights are the highest when you're at the beginning of the mortgage, and that's pulling that duration down below 180. Okay, now let's consider duration of a portfolio. What if you have a whole group of assets, say a whole bunch of bonds that had, differing effective rates and different coupon dates and different maturities? How are you going to figure duration for that? Well, a couple of possibilities here. You could look at your total cash flow of the portfolio at each time here and apply your MACD or MOD formula, whichever one you're interested in. But that's going to be complicated because you've got all the different maturities and different coupon dates, and then coupons will be dropping off as they're paid, and so that can get very complicated very quickly. Another possibility is that you could find the duration of each asset or each bond that's in the portfolio, and then you could take a kind of average of all of those durations. And in fact, that's what we'll do. We'll take a weighted average where you weight by the present value of the bond payments. In other words, you're going to weight by the price of that bond at the interest rate that you're going to use to calculate duration. So what we're going to do is we're going to take the duration for the first security and multiply it by the price. Okay, so this is a price weighting. Weight the duration by the price. And then the second security, just consider 2 securities for now, and we're going to weight that by the price. And then we're dividing by the total price here. So this is how you do a weighted average. Well, let's consider an example here. Let's say that we've got 3 bonds in a portfolio. The duration of these bonds are 2, 4, and 8 years, respectively. And we know that the price of the first bond is half the second, and the price of the second bond is the same as the third. Let's determine the duration of this entire portfolio. Okay, so, duration is going to be the price-weighted average of the durations of the individual securities. So we're going to take the first price times the first duration, second price times the second duration, third price times the third duration, divide by the total prices. Well, we don't know what the total of all the prices are, but we do know some relationships in between them here. We know that the price of the first bond is half the second here. So we know that P1 is 1/2 of P2, or if you want the second bond, P2 is twice the first bond, P1. And then we know that the price of the second bond is the same as the third bond. So we also know that the price of the third bond is the same as the price of the second, which is going to be twice the price of the first bond. So now we've got some relative prices in here. So let's go ahead and do some plugins with relative prices here. We know that the duration for these bonds are 2, 4, and 8 years respectively. So MACD1 is 2, MACD2 is 4, and MACD3 is going to be 8. So the price, everything's based on the price of the first bond. P2 depends on P1, and then P3 depends on P1. So we'll write everything in terms of P1. So first price times the first duration, 2, plus, and then P2 is twice P1. So P2 is 2P1, and then times the duration of the second bond is 4, plus the third price is again 2P1, and then times that duration, which is 8, and then divide by the total price, P1 plus P2 is 2P1, and P3 is also 2P1. And then notice that P1 is a common factor across the bottom and across the top, so we can actually just cancel everything out here if we wanted to. We can factor out and cancel the P1 on the top and on the bottom. So what's left here is a 1. So what we've got left then is 2 plus 2 times 4, 8, plus 2 times 8, 16. So 2 plus 8 plus 16 upstairs. And then downstairs, 1 plus 2 plus 2, 5. So this is just 26/5, which as a decimal is 5.2. So 5.2 years. And you could do that with any number or combination of securities. And then if we wanted to do modified duration, we would do the same thing here, except this would be mod D1, mod D2, and mod D3. Now to finish up here, I want to finish up the first part of Chapter 9. I want to look at how duration changes with time. So if we write out what Macaulay duration is, it's the first cash flow times v to the first times 1. This is if you're at time 0. Plus second cash flow v squared times 2 all the way up to the last cash flow at time n, v to the n times n. And then you're dividing by the sum of the present values of the cash flows. So we want to ask what happens as the time of the first cash flow approaches. So you're starting at time 0 here. And then at time 1, you're going to have a cash flow. So this is going to be CF1. And I'm asking what happens to this ratio here as t approaches time 1. Well, if we look at a variable expression for this first cash flow, let's call it CF1 v to the t times t, where t is going to be the the elapsed time between 0 and 1. Notice that as t approaches 1, the time remaining until that cash flow occurs goes to 0. So this t right here goes to 0. And then v to the t is actually starting to look like v to the 0, which is 1. So we've got a constant times something that's approaching 1 times something that's approaching 0. That's going to approach 0. So this first cash flow up here, as t approaches 1, that is approaching 0. And all these cash flows are decreasing too because the duration, the time till they occur, is approaching 1 less. So this one is approaching CF2V times 1, all the way down to this one is approaching CF and V to the n minus 1 times n minus 1. So all those are decreasing. And these present values on the bottom, those are also decreasing. But what happens is, as you get close here, this is approaching 0. Okay, this one's not approaching 0. It's decreasing, but it's not approaching 0. Okay, now think of what happens just after that payment occurs. Okay, well, this is already pretty close to 0. Just after that payment, this cash flow drops off. Okay, and so that means that we're taking out something that's really close to 0. So the numerator doesn't really change that much. But this cash flow, CF1V, this present value of this cash flow, is going to drop out of the denominator. That's going to make the denominator smaller, which is going to make the ratio bigger. So if we actually look at a graph here over time of what happens to the Macaulay duration, what happens is as you approach time 1, the time of that first cash flow, your Macaulay duration is decreasing. Okay, the numerator and the denominator are both decreasing, but the numerator is decreasing a little bit faster. But then at time 1, when that cash flow in the denominator drops off, because once that cash flow is made, then it's no longer needed to calculate the present value of the remaining cash flows. Then Macaulay duration is going to jump up. And then it's going to start this long decrease again until the time of the next cash flow. And then the second term is going to drop off the bottom while this one's approaching 0. And then duration is going to jump up again. And then it's going to decrease and jump up, and you'll get this sawtooth pattern. Now, in finance, though, we don't like sawtooth functions. They're messy functions. So we actually look at things in a different way to approximate this with a smooth function. But just wanted you to think about that process and what happens just before and then the instant after that cash flow is made, and what happens to this fraction when that term drops off at the bottom.